Okay. All right, number 1, the internal energy of a system. A, B, C, D, or E?
B.
Yes, that's correct. The answer is B. It's the sum of the potential and the kinetic energies of the components of the system. Which of the following is an exothermic process? Again, A, B, C, D, or E?
A.
Yep, condensation is an exothermic process. Very good. Okay, the value of delta H for this reaction here is a negative 186 kilojoules. The value of, oh, so here they want the heat of formation for HCl gas. So what you need to do is you need to divide the coefficients here by 2. So we're going to have 1/2 hydrogen gas plus 1/2 chlorine gas, and that'll give us 1 mole of HCl. Okay, so they said for this reaction, it's a negative 186. For this reaction here, it's a negative 186 joules. So basically what we need to do is divide the negative 186 by 2, and because we divided the coefficients by 2, so a negative 186 divided by 2 is a negative 93. So the answer here is C. So it's a negative 93 kilojoules. Okay, again, if you have a question, go ahead and ask as I go through, as I'm going through this. You can use the chat or you can use the microphone, either one. All right, the molar heat capacity of a compound with this formula is 88 joules per mole Kelvin. The specific heat of this substance is, so they give us the molar heat capacity of this compound, okay, and the specific heat of this substance is, oh, yeah, they're giving us the molar heat capacity. Sorry, I'm really tired and down and everything else. Okay, so we just need to convert this to, we have 88 joules per mole Kelvin. We need to convert this to joules per gram Kelvin. So we need the molar mass of the compound. So 1 mole of the compound, we have 2 carbons. That's 2 times 12.011. And we have 6 hydrogens. 6 times 1.00794. We have a sulfur. I can't ever remember it. Sulfur, I think, is 32. Let's see. Sulfur is, 32.066. So 32.066 plus 1 oxygen, which is 15.9994. And I get 78.1 grams. Moles cancel, and we'll be left with joules per gram Kelvin. So 88 divided by 78.1, that's 1.13 joules per gram Kelvin. And the answer here is D. Okay, let's do this next one. the combustion of titanium with oxygen produces titanium dioxide. So when 0.61 grams of titanium is combusted in a bomb calorimeter, the temperature of the calorimeter increases from 25 to 50.5 degrees Celsius. So in a separate experiment, the heat capacity of the calorimeter is 9.84 kilojoules per Kelvin. The heat of reaction for the combustion of 1 mole of titanium in this calorimeter is how many kilojoules per mole? Okay, so what we want is the heat of combustion. Okay, and so remember, the calorimeter is going to absorb, some energy here, and then plus we need to use the heat capacity of the calorimeter. So what we'll do is we'll go from, we can find Q for the titanium. Yeah, so Q for the titanium plus Q, or the heat capacity of the calorimeter, is going to give us, well, what I should do is add them all together. That's going to give us the heat of combustion, okay? And that's going to be equal to 0, so the heat of combustion is going to be equal to negative Q, the titanium, minus that of the calorimeter, okay? So let's see. So the Q of combustion is going to be equal to a negative Q for the burning the titanium. It's going to be 0.61 grams. And oh, this is strange. We don't have a we should have a, oh, okay. So, no, that's in kilojoules per Kelvin. Yeah, this problem, I feel like we're missing some information here. Any suggestions here?
Wouldn't we just do 50 minus 25 and then multiply that by 9.84? And then
Kilojoules per mole. And then we'd have to multiply.
And then we would have to do 0.610 divided by the molar mass of titanium, and then we get 0.0127 mole, and then we do 250.92 divided by the mole.
Yeah, but I still feel like we're missing some information here. Is this in, in kilojoules per mole? All right, so we can, we can convert the 0.61 grams of titanium to moles of titanium. That's fine. And then get delta T. And then multiply by the 9.84 kilojoules per Kelvin. So let's see here. We have point. I still think we're missing something here. I don't know. I'm really tired. 0.61 grams of titanium. Does anyone know the molar mass of the titanium?
Yeah, it's 47.867.
I'm sorry, it's what?
47.867.
47.867. Okay. So 47.867 grams. Whoops. Oh, come on. Per mole. So that'd give us the moles. So 0.61 divided by 47.867. I get 0.0127 moles, and then delta T is going to be 50.50 degrees Celsius minus 25 degrees Celsius, and that'd just be no. That'd be minus the 25. That'd just be 25. Oh my gosh, that'd just be 25.5 degrees Celsius. Okay, so we have the delta T, and we'd have to multiply. Okay, and we want that for 1 mole of the titanium. So we go ahead and we have the 0.0127 moles. And here we have 9.84, and that'd be kilojoules per mole. And then we have our delta T, which is 25.5 degrees Celsius. And let's go ahead and calculate this, and then that's just going to be for the 0.0127 moles. So 0.127 times, I don't want to spend too much time on this, times 9.84 times 25.5. Okay, so, and this, you know what, the delta T, this is the same as Kelvin because it's a temperature difference. So, what is this? Kilojoules. Oh, kilojoules per Kelvin. Okay. Oh boy. Okay. So we have, you know what? I need to look at this problem. I'm not gonna continue with this. I'll do it and I'll put it on a quick video when my head is a little clearer here.
Is the correct answer B though?
I don't know. For number 5, I don't know. I don't have the answer key in front of me, but I'll take a look at this one later. Okay. I don't know. Let's do number 6. I'll look at this one probably tomorrow, and I'll just do a video. I just kind of messed up here pretty bad, and I just don't want to, we've already spent 5 minutes on it, so I'll redo this one. Okay, so I'm sorry, that was number 5. Okay, number 6, calculate the work in kilojoules done during a reaction in which the internal volume contracts from 83 to 13 liters against an outside pressure of 4.4 atmospheres. So our work is equal to a negative it should be a negative P times delta V, a negative P times delta V. So let's see. The pressure is 4.4. Don't forget the negative sign. Atmospheres times delta V is going to be 13 liters minus 83 liters. Okay. We put this into the calculator. Negative 4.4 times 13 minus 83. And I have 308, and that's liters per atmospheres, okay? So we're asked to do this in kilojoules, so we need to convert this to kilojoules. So we have 308 liters atmospheres, and 1 liter atmosphere is 101 joules, and then we have 1,000 joules is 1 kilojoule. And we put this in the calculator. That'd be 308 times 101 divided by 1,000. Okay. And I get 31. I get 31 kilojoules. So the answer for that one is, I only see a negative 31. It's definitely a positive. Oh, okay, A, 31 kilojoules. So you have to watch your, well, include that negative sign and make sure that you calculate delta V. Given the data in the table below, the standard enthalpy change for the reaction, so here's the reaction, is how many kilojoules. So we start with the products, and then we'll start with the 4 moles of nitrogen monoxide, and we'll multiply that by 90 kilojoules per mole. And then we'll add to that 6 moles of liquid water. And that's a negative 286 kilojoules per mole. I'll put that in brackets, and we're going to subtract from that the reactants. We have 4 moles of ammonia times a negative 46 kilojoules per mole. And we have 5 moles plus 5 moles. I think we did something like this one in class. 5 moles of oxygen. And I would expect you to know that the standard enthalpy of formation for oxygen gas is 0 kilojoules per mole, because that's in its most stable state. So we put this in the calculator. We have 4 times 90 plus 6 times a negative 286, and that's going to be minus 4 times a negative 46. And I get a negative 1,172 kilojoules. So B is the answer. Okay. The specific heat capacity of a metal is 0.13 joules per gram Kelvin. How much heat in joules is required to raise the temperature of 15 grams of this metal from 22 to 37 degrees. So here we'll use, let's see, Q is equal to the mass times the specific heat capacity times delta T. Okay, so Q is equal to the mass, 15 grams, times the specific heat capacity, which is 0.13 joules per gram Kelvin, times delta T, which would be 37 degrees Celsius minus 22 degrees Celsius. Remember, this will be either equal to degrees Celsius, and that's going to be the same as the Kelvin units because it's a temperature difference. So we have 15, whoops, my calculator is upside down, 15 times 0.13 times 37 minus 22, and I get 29 joules. So the answer would be E for number 8. Okay, yeah, we'll do this one. The value of the standard enthalpy for this reaction is 128.1 kilojoules. How many kilojoules of heat are consumed when 5.75 grams of carbon monoxide is formed, as shown in the equation? Make sure your equation's balanced. It is. So we need to convert the 5.75 grams of carbon monoxide to moles. So that's going to be 12.011 plus 15.9994. So the molar mass of carbon dioxide or carbon monoxide is 28.0 grams per mole. And then we use our balanced chemical equation. We have 1 mole of carbon monoxide, and so this would give us 128, positive 128.1 kilojoules. Okay, so it cancels. It's grams of CO. That cancels. 5.75 divided by 28 times 128.1, and I get 26.3 kilojoules. And there it is, D. Give me 1 second, or a few seconds here. I got to go stir the dog food. Be right back. Okay. Okay, dog food is stirred. You know, it's funny. My husband used to do all this while I was doing my reviews. You know, he used to get the food ready, feed the dogs, give Layla her shot, and all that. Oh well. I'm sorry. This has been it's rough. Okay. This reaction.
If you need to take a couple minutes, do that, please.
Yeah, I'm fine. The reaction, okay. So this reaction is, all right, we have a negative delta H, and heat is either released or absorbed. So delta H is negative, so we have an exothermic reaction, and heat is released. So number 10 is exothermic heat is released. A. Okay. Under what conditions is the enthalpy change of a process equal to the amount of heat transferred into or out of a system? Ouch. So we have these three choices here. So would you choose A, B, C, D, or E?
B.
You said B or D?
B as in boy.
B. Okay. And that's true. It's when the pressure is constant. So the answer would be B only. Okay. Let's see. This one's good. Number 12. For which one of the following reactions is the value of the standard enthalpy of reaction equal to the standard enthalpy of formation for the product? So it'd be one of these reactions, A, B, C, or D or E. What do you guys think? Okay, well, let's take a look. So I look at the first reaction, and I see that this is for 1 mole of product from its elements. Second reaction, 1 mole of product from its elements, right? Same with this one, same with this one. So the answer here would be all of them. So the standard enthalpy for the reaction is going to be the same or equal to the standard enthalpy of formation. Remember, the standard enthalpy of formation is for 1 mole of product from its element. Okay, so let's go
I have
here.
a question.
Sure.
So is there like a way to like determine like the because it's like you said it's all the above, but like does it also like depend on the states?
Oh, and the states of the substances in the reaction?
Yeah.
No. I mean, well, yes. Hold on. The reactants, right, have to be the elements in their standard form. Okay. So for all of these elements are all in their standard form. Okay. So for example, oxygen, the standard form of oxygen is oxygen gas. Ozone, and this is also a gas, is not the standard form of oxygen. Same with carbon. The standard form of carbon is graphite. In fact, its enthalpy, its standard enthalpy of formation is equal to 0. Same here. Ozone is going to have some, it's not going to be 0. It's some other value. And the same here, like for diamond, right? Both are solid carbon. But this is the standard form of carbon. And the standard enthalpy of formation is equal to 0. For diamond, it's a value other than 0. So yes, it is important. As far as the products go, no, you can have a liquid, solid, or gas. Like I might ask you, well, let me think here. Oh, darn it. I might ask you to write me the formation equation for potassium chromate. Okay, so what you would do is you go ahead and write the potassium chromate, and this is a solid, by the way, and then we would just go ahead and write the standard form forms of the elements. So we have 2 potassium. This would be 2 solid potassiums. We have 1 chromium. This would be solid chromium. And we have 4 oxygens. So this would be 2 diatomic oxygens. Okay, so this is a formation equation. It has 1 mole of product from its elements in their standard form. The elements must be in their standard form. Okay.
Thank
You guys having, you're welcome. Are you guys having problems accessing the Pearson text? I just saw the chat. I don't believe there are any problems with it tonight. So if you're having trouble accessing it, what you need to do is you need to take a few steps. You need to log out, clear your computer cache, and then you need to shut down your computer, and then turn on the computer, log back in, and make sure you're using Chrome browser. I have an Apple here at home. Safari browser does not work well. Okay. We've already done one like this. Basically, the standard enthalpy change for this reaction. Make sure the reaction is balanced. And let's see. It says the standard enthalpy change is a negative 72.8 kilojoules. What is the standard enthalpy of formation? We just did one like this. You would go ahead and divide the coefficients by 2, and then you would need to divide this by 2. So that would be a negative 36.4 kilojoules. Okay. Oh, here's one for you. You guys can answer this. Given a 1 gram sample of each of the following metals at 50 degrees Celsius, which would raise 100 grams of water at 25 degrees to the highest temperature? So,
A.
Yep, actually, let me see. Yeah, actually it would be A. And what we're looking at are, is the specific heat. And so this one here has the highest specific heat. So this would, raise the water to a higher temperature. Okay. When an exothermic reaction is carried out in a coffee cup calorimeter, which statement is correct?
D.
Yes, D would be the correct answer. The enthalpy of the products is going to be lower than the enthalpy of the reactants. Okay, because we haven't, the reaction is our system. Okay, and the water and everything else would be the surroundings. So if it's an exothermic reaction, then the system, right, is releasing heat into the surroundings. So in that case, then, this would be incorrect. This would be incorrect because the reaction is releasing heat. The temperature of the water decreases? No. And then the enthalpy change for the reaction is positive? No, we were just told it's exothermic. It would be negative. Okay. How many sigma bonds are there in the following structure? So let's see. And how many pi bonds? How many pi bonds are in this structure?
3 pi bonds.
3 pi bonds, yes. You have 2 pi bonds and the triple bond. So we have 3 pi bonds. So it's going to be between this one and this one. So how many sigma bonds?
11 sigma bonds.
Yep. Hold on. 1, 2. Yep. 11 sigma bonds. So the answer here would be D. Oh, this is one of those Hess's law. Hess's law. We're asked to determine the enthalpy change for this reaction here. And we're given this data here with the delta H's for each reaction. So what we want to do is manipulate these reactions so that when we sum them, we end up with this overall reaction. But remember, if we reverse a reaction, we have to change the sign of delta H. If we multiply a coefficient by a number or, including a fraction, and we would do the same with delta H. Let's see. So this first one here, this first one, I'm going to leave this first one alone. I'm not going to do anything with it. Okay, so I'm doing nothing here with this one. And let's see. This reaction here, I'm going to reverse it because we have 2 nitrogen monoxides as reactants here. So I'm going to reverse this equation here because we want the nitrogen monoxide as a reactant. And then this one here, okay, so I reverse this one so the nitrogens will cancel out. Okay, that's good. Do I need to? No, I don't need to do anything with this one either. So I'm just going to reverse this one. So let's see, we have the 2H2 plus O2, 2H2O. Delta H is a negative 571.6 kilojoules. These are kind of fun to do. And then we're going to reverse the second one. So we have 2 nitrogen monoxide gas. That'll give us nitrogen plus, this one was an easy one. And then I'll just leave this one alone too. So here, delta H, remember I have to change the sign. This is positive, so now it's going to be negative. So it's a negative 180.5 kilojoules. And then I'll just leave this one too, nitrogen plus 3 hydrogens to give 2 ammonias. And I'll just leave delta H alone. That's a negative 92.22. Oh, come back. Okay. Kilojoules. All right, let's see here. Okay. Oh, come on. Kilojoules. Okay, so now we'll go ahead and let's see. We have 2 and 3. So that's 5 moles of hydrogen. And let's see if anything cancels out here. The nitrogens cancel out and the oxygens cancel out here. So I have the 5 hydrogens plus the 2 nitrogen monoxides. And then I have the 2 waters and 2 ammonias. So 2 moles of ammonia plus 2 moles of the water. And then I just go ahead and add the delta H's. So was that a negative 570? Yeah, negative 571. Negative 571 plus a negative 180.5 plus a negative 92.22. And that gives me a negative 844. I get a negative 844 kilojoules. So that looks like B is the answer there.
Can you explain the 11 sigma bonds?
The 11 sigma bonds? Yeah. So, okay. What you should do is, if you're given a larger molecule like this, is go ahead and draw it out. take the time to do that. And you have the carbon triple bond, you have the carbon oxygen double bond, a carbon, and then 3 hydrogens. Okay, so this makes it a lot easier. You went to sigma bonds, sorry. Triple bonds and double bonds both have 1 sigma bond. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 sigma bonds.
Okay, thank you.
You're very welcome.
What are the
Okay.
pi bonds? Are they
The pi bonds, a double bond has 1 pi bond and 1 sigma bond, and a triple bond has 2 pi bonds and 1 sigma bond. Okay,
Okay, thank you.
you're welcome. Remember, the pi bonds they're from the side-to-side overlap of those p orbitals. Okay, they're not as strong. A pi bond is not as strong as a sigma bond. In fact, in chemical reactions, you'll find out in organic chemistry that usually in most reactions, I'm not going to say all reactions, but in most reactions, the sigma bonds will break first.
Also, for 17, how do you know when to reverse the equation?
Let's see, we reverse this one. The reason I reverse this equation is because here in the equation that we're looking for delta H, the nitrogen monoxide is a reactant. Here it's a product, so I have to reverse it.
I see. Okay, thank you.
Yeah. They're fun to do. They're like a little puzzle. What is the angle between 2 sp2 hybrid orbitals?
B, 120.
Yeah, because remember, sp2 hybridization corresponds to a trigonal-planar geometry. sp3 hybridization corresponds to a tetrahedral geometry. And we're only looking at electron pair geometries. And an sp hybridized orbital, that corresponds to a linear geometry.
For the
go ahead.
So for these types of questions, like on the exam, like we would just have to like we wouldn't get like a sheet or anything, right? Like it would just be like you would just have to be like, okay.
Yeah, you just need to remember. Yeah.
Okay.
Okay. So which orbitals overlap in forming the bromine carbon sigma bond of this bromine cyanide bond? Okay. So what you want to do is you want to draw the Lewis structure. Okay. So let's see. We have 7 plus 4, 11 plus 5. We have 16 electrons to distribute. I'm going to go ahead and distribute them around the peripheral atoms first. 2, 4, 6, 8, 10, 12, 14, and 16. I'm going to go ahead and move a lone pair of electrons over to the carbon because the carbon does not have an octet. And carbon still doesn't have an octet. So I'm going to move another pair of electrons over to the carbon. Okay. So we see that the carbon has a triple bond and this single bond. So what we're interested in is the overlap between this carbon and the bromine. Okay, so this is what is the hybridization of this carbon here? What is the geometry? What is the electron pair geometry here?
sp3.
No. What is the electron pair geometry? of this carbon? What is the
Linear?
electron? It's linear. So the carbon then would have what type of hybridized bonds?
SP.
SP. So what we have is we have overlap of an SP hybrid orbital, and we're looking at the bromine. And so the bromine, this would just be, you know, if you look at the periodic table for bromine, let's take a look here. Bromine. Okay, this is going to be a 4p orbital, unhybridized orbital. So what we have is overlap between, you know, we have the 4p unhybridized orbital of bromine with an sp hybridized orbital of carbon. So the answer here would be D. Okay.
Wait, how would the carbon element be linear?
Well, you've got a central carbon atom. I mean, this whole thing is linear. You have a central carbon atom bonded to two other atoms in 0 lone pairs. So this would be a linear electron pair geometry and also a linear molecular geometry. Okay. So review your electron pair geometries and your molecular geometries. But, you know, when we're doing, when we're looking at this overlap, we're only, and hybridization, we're only looking at the electron pair geometry. Okay. Okay. What is the maximum number of sigma bonds that can form between two atoms?
Is it A?
Yeah, just one. Okay. So you'll never have more than one sigma bond form between two atoms. Now, you could have a double bond where you have one sigma and one pi bond, or you could have a triple bond where you have one sigma and two pi bonds, but you'll never have more than one sigma bond between two atoms. Okay. The hybrid orbitals used by carbon and carbon dioxide are,
A.
you got to draw, you got to draw your Lewis structure, right? But yeah, and we look at this, it's linear, so it's sp hybridization. A, you are correct.
What does the D mean?
The D?
Yes.
Oh, this one here, sp3d.
Yes.
That'd be a hybrid orbital that is composed of, where we've mixed an s, 3p orbitals, and 1d orbital. So 1s, 3p orbitals, and 1d orbital to form a hybrid orbital. Okay. Okay. The boron atom in the BF3 molecule is, again, you gotta draw your Lewis structures. And I'm not going to draw the electrons in around the fluorine, but the what would the, I mean, would the boron atom, would it have unhybridized orbitals, or sp, sp2, or sp3 hybridized
SP2?
orbitals? Yep, sp2. And the reason why is this is a trigonal planar electron pair geometry, and that corresponds to sp2 hybridization. Good. Oh, let's see. What is the proper order of decreasing F angles in the compounds below? So we already have our BF3, and these angles, whoops, these bond angles are 120 degrees. And then we have the beryllium fluoride. So we have beryllium. We have the two fluorines. And so what we have are, I'll go ahead and put the electrons. Remember, fluorine only forms one bond. So let's see, 14, 16, 2, 4, 6, 8, 10, 12, 14, 16. So we put our 16 electrons around this. And what is it asking? Oh, so this is 180 degrees because this is linear. And then CF4, I mean, this is tetrahedral. So the bond angles are 109.5 degrees. So what's it asking? Oh, decreasing bond angles. So what we have is the, okay, so what we have is we have the beryllium fluoride. Okay, beryllium fluoride is going to be greater, has a higher bond angle than the BF3, which is number 2, and that's a higher bond or greater bond angle than the carbon tetrafluoride, which is number 3. So that'd be, why do I have 2 2s here? Oh my. So let's see, we have 180, so BF2 is number 2, and then we have the 120, so that'd be the BF3, so that'd be 1, that'd be number 1, and then 3, so 2, 1, and 3, so the answer here would be E. Okay, so that'd be E. That was, okay, number 24. You guys answer this. Which of the following molecules are polar? Again, you need to draw those Lewis structures. What do you think?
E?
So E. All right. So
Possibly.
okay.
Or J.
Well, let's take a look. Okay. So you said E. So I'm going to go ahead and draw E. So we have Cl, 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 and I'm not going to put the electrons on the chlorine, but this is a trigonal bipyramidal, right? And we have that. We have the equatorial bonds, and then we have our axial bonds here. So these, this has got loads of symmetry here. This is symmetric, so this is non-polar. Okay. Carbon dioxide, same thing. It's non-polar. It's linear. Both bonds are polar, but think of it as a tug of war, right? These are being, the electrons are being pulled in opposite directions. So this is not polar. So that one's not polar. That one's not polar. The boron trichloride, 1, 2, 3, same thing. This is trigonal planar. The boron chlorine bonds are polar, but each one of these bonds points to the corner of an equilateral triangle, and so any dipole cancels out. So that's not, and carbon tetrachloride is tetrahedral, right? And oh boy, that's not, okay, it doesn't matter. And again, each one of these bonds is pointing towards the corner of a tetrahedron. So this is not polar. So SO2, let's see what we have here. This one here, let's see, we have 18 electrons. I'm going to go ahead and put those. I have to do that here because I want to show you. So sulfur needs an octet. So I'm going to go ahead and grab a pair of electrons from this oxygen here. It still needs. Oh, wait a minute. Wait. Let me. No, I forgot to. I have to count the number of electrons here. 2, 4, 6, 8, 10, 12, 14, 16. Yeah, that looks better. Okay, I have an extra pair of electrons, so I have to put it on the sulfur. So you got this lone pair of electrons. This has a bent geometry. So because of this lone pair of electrons, this is going to be polar, okay? Because, I mean, you've got the oxygens that are more polar than sulfur, pulling those electrons. Those electrons are being, they're more attracted to the oxygens, right? But because of this lone pair of electrons, this is not linear, it's bent. So this would be a polar molecule. Okay.
So what would the electron geometry for SO2 be?
What would it be? You have the electron pair geometry. You have 1, 2, 3 charge clouds,
So
2 are bonds,
trigonal.
and yeah, you'd have a trigonal planar electron pair geometry. You have 1 lone pair, so it's a trigonal planar electron pair geometry, but it's a bent molecular geometry.
Okay, thank you.
Mm-hmm. Okay. I got to go for about 5 minutes because I have to feed my dogs and give Layla her shot. So why don't you guys figure out number 25? I'll be back in 5 or less. I'll just feed them. that was quick. Okay, I'm back. Oh my goodness. They're eating, so I'll wait. Okay, anybody figure out number 25?
A.
Let me see. Yeah, I think that, yeah. So what we have is, oh, come on. So what we have is we have 3 iodines, and we'll put a negative sign here. So we go ahead and we put the electrons around the 2 peripheral atoms. Okay, so let's see. We would have 7 times 3 is 21, plus 1 electron for the charge, so it's 22 electrons. So I've used 2, 4, 6, 8, 10, 12, 14, 16. So we put 2, 4, 6 electrons on the iodine. Let me, 1, 2, 3. So iodine has 1, 2, 3, 4, 5 charge clouds. And so this would be trigonal bipyramidal. It has 5 charge clouds. That would be the electron pair geometry. Can anyone tell me what the molecular geometry of this would be?
Linear.
It is linear. The molecular geometry is linear. Okay. Let's see. According to the SEPR theory, the shape of this ion is described. Again, you just want to
D.
Square planar. Okay, let's see. 1, 2, 3, 4. I'll just put the chlorines. Oh dear, that's okay. Chlorine, 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 and we have a total of 4 times 7 is 28, plus 7 electrons for the iodine. 28 and 7, that's 35, plus 1 electron for the charge. We have 36 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So at 24, 26, 28, 30, 34, and wait a minute. Oh, I don't believe so. 6 times 4 is 24, 26, 28, 30, 32, 34. So I need to put 2 lone pairs on the iodine. So 2 lone pairs on the iodine. I'll go ahead and, yeah, do that. So, and I should have brackets around this. It's an ion. So the shape, there are 6 charge clouds. 6 charge clouds, but they want the shape, not the electron pair geometry. This would be octahedral as far as the electron pair geometry, but because of those 2 lone pairs of electrons on the iodine, what you're correct, we have a square planar molecular geometry. Shape and molecular geometry are the same thing, okay? Oh, which one of the following would have bond angles of approximately 170 degrees? Or, I'm sorry, 107 degrees.
I think it's NH3.
Yeah, because remember, if you have a tetrahedral geometry, the angles are 109.5. Well, ammonia, it has a tetrahedral electron pair geometry. There are 4 charge clouds. But remember, this lone pair of electrons compresses these bonds, and it compresses them to about 107 degrees. With water, oh gosh, I cannot draw. I never could. I always wanted to, but doesn't happen. Okay. Water, it has a tetrahedral electron pair geometry, has 4 charge clouds, but now we've got 2 lone pairs, so this angle is compressed even more. That's about 104.5 degrees. Okay. Okay. For a process of constant volume, what can we say about work? And, well, what can we say? For a process at constant volume, what can we say about it? Well, remember, work, right, is equal to pressure volume work, right? Negative pressure, or negative P delta V. So if the volume is constant, then that's going to mean that the work, if this is constant, the work is going to be 0. So A would be the correct answer. Work is 0, and delta E would be equal to the heat. Okay. Okay, let's see.
Dr. O'Connor,
Mm-hmm.
I'm sorry, but going back to 26,
Okay.
Is there an extra pair of electrons on iodine?
There are 2 lone pairs of electrons on the iodine.
Oh, okay. Sorry.
Yeah, we have 2 lone pairs on the iodine. So this is an octahedral electron pair geometry, but because of the 2 lone pairs of electrons, it's a square planar molecular shape or molecular geometry.
Okay, thank you.
You're welcome. Okay, this is the drawing for number 29.
So was that answer for 27 NH3?
Yes, yeah.
Okay.
Yeah, because the ammonia has a tetrahedral electron pair geometry, but it has the lone pair, and this lone pair compresses these bond angles to about 107 degrees. And then I showed water that has 2 lone pairs that compresses this bond angle even more, actually down to 104.5 degrees. Okay, so yeah, it's definitely the ammonia. Let's see. So that'd be the answer there would be C. I forgot to circle that. Okay. So here we have acetic acid. Okay. So a partial positive charge would occur on which atom or which atoms? Okay. So what do you think? Partial positive charge would occur on, well, you've got this polar bond here, and you have this oxygen, right, that's bonded to both the carbon and the hydrogen. So basically, you're going to have, this oxygen, these electrons in the bond are going to spend more time around the oxygen. It results in a partial positive charge on the carbon. That'd be carbon B. And then, same here. This oxygen is pulling the electrons, or the electrons in this bond and in this bond are going to spend more time around the oxygen. So that's also going to result in a partial positive on the hydrogen. So the answer would be both B and D. So the answer here would be C. Okay, I gotta go give Layla her shot. I'll be back in 2 minutes. So you guys figure out which one of these is paramagnetic, and I'll be right back. Okay, I will be back. All right, Layla, we're gonna have her shot. Okay, you're done for now. Oh my. Okay. All right, we're done. Okay. So, which one was paramagnetic?
I think it's A.
A. So let's see. Yeah, I think so too. Yeah, I think so too. What you would do is, let me see. Do I have another diagram here? Okay. Anyway, Where is it? Here it is. Okay. Yeah, so we have the nitrogen. So basically we have 2 nitrogens, and each nitrogen has 7 electrons, so that's 14 electrons plus 2. That's 16 electrons. So 2 will go here, 2 will go here. Now we have to fill this up differently. So this is the 1s, this is the sigma 1s, this is the sigma 2s. So sigma star 2s. I'll just put the star right here, and we'll put 2 electrons in there. Okay. And then we have the sigma 2s, or sigma, I'm sorry, this is the sigma 1s. Okay. Sigma star 1s. And I don't have enough room here. Oh my, let's do it over here. Okay, the 1s, we have the sigma 1s, sigma star 1s, and then we have the sigma 2s fills next, and then the sigma star 2s. And then if you remember from, well, if we go here to our lecture, okay, remember from lithium to nitrogen, after the sigma star 2s fills, then we have the pi 2p orbitals that fill. Remember, from oxygen to nitrogen, after the sigma star 2s, it's the sigma 2p that fills, and then the pi 2p orbitals. Okay, so we're going to fill the pi 2p orbitals first. Oh no, here we are. Okay, so we will, so here we go, over here. Okay, and then I have the pi 2p orbitals. So let's go ahead and start filling. So we have 2, 4, 6, 8, 10, and then how many electrons? We have 16. Okay, so we have 2, 4, 6, 8, 10. Wait, 2, 4, 6, 8, 10, 12. Okay. Okay. And then after the sigma 2p, we have or after the pi 2p, sorry guys, that should be the pi 2p. Oh God, let's see here. Okay. I'm trying to go too quickly, and that never works. Okay, so after the pi 2p, then we have the sigma 2p, and so we'll put 2 electrons in there. So that'll be 14, and then we have the pi star 2p. So the pi star 2p, so this would be pi star 2p. We have 2 electrons left. Remember, we cannot fill the orbitals until both of these are half filled. So we have 2, 4, 6, 8, 10, 12, 14, 16 electrons. So yes, this would be paramagnetic because we have the 2 unpaired electrons. So let's see. Yeah, so the answer, you're correct. The answer is A.
Can you send 29 for the diagram again?
Number 29
Yeah, for the diagram.
for this?
Yeah, like where you said the positive.
Yeah, because you've got, okay, you have this carbon carbon-oxygen double bond. And so the oxygen is more electronegative than the carbon, okay? So the electrons are going to spend more time around the oxygen in the bond, and that is going to result in a partial positive charge on the carbon, okay? And then remember, here you've also got this carbon-oxygen single bond. Again, the electrons are going to spend more time around the oxygen here. Again, you have a partial positive on the carbon, but here you have an oxygen-hydrogen bond, and the electron, oxygen is more electronegative than hydrogen, right? So those electrons are gonna spend more time around the oxygen, and that'll result in a partial positive charge on the hydrogen, okay?
Okay, thank you.
Yeah, does that make sense?
Yeah, it makes sense.
Yes. Yeah.
For number 30, wouldn't nitrogen only have 12 electrons?
Well, nitrogen has, what is the atomic number of nitrogen?
Oh, yeah, it is 7. So,
7, right? It's
yeah.
7. So you've got 2 nitrogens, that's 7 and 7 is 14, plus the -2 charge, so we have to add 2 to that for that -2 charge.
I have a question. So for the this might be a stupid question.
There are no stupid questions.
But how come, like, when we're drawing Lewis structures, then we look at the group for electrons, but then here we're looking at the atomic number?
Because we need to know how those electrons are distributed in the molecular orbitals.
Oh, is it
right?
because we're looking at the SP, like from the periodic table, like the SP?
No, you're basically looking, we basically have, okay, you know how you do electron configurations? We have a filling order, right?
Yeah.
1s and then the 2s, then the 2p, and on and on and on, right? Well, it's the same with molecular orbital theory. We have a certain filling order.
Mm-hmm.
So you need, first we find the total number of electrons in the substance, okay? In fact, you know what? Just for fun. Oh, darn it. No, I shouldn't have done that. Okay. In fact, why not? We'll do this now. Can anyone tell me the bond order for this here? Layla, what do you want? She's scratching at the door. She's funny.
I also think that the MO diagram, like, I think it's a little confusing. Like, I don't like, I know how to get the answer, like, but I don't know how to, like, read off the diagram. Like, you know how in 31 there's, like, the diagram?
Yeah, so I did the diagram here, right? Is that what you're looking at? Oh,
yeah.
Okay. Yeah. Oh. Okay. Yeah, we start, first we fill the sigma 1s. Remember, for each molecular orbital, or when we combine these molecular orbitals, we're going to have a bonding and an anti-bonding orbital. So here we have this, the sigma 1s is lower in energy than the sigma star 1s. So the sigma 1s fills first, and then the sigma star 1s fills, and then we have the sigma 2s fills, and then the sigma star 2s fills, and then it gets a little bit more complex as we get to the pi 2p and the sigma 2p.
So the ones that are starred, they're like anti-bonding?
Yes. So in order to determine the bond order, that's going to be 1/2 times the number of electrons in bonding orbitals. So that'd be 2, 4, 6, 8, 10. Layla, what are you doing? So that'd be 10. And then here we have the and that's going to be minus the number of electrons in the antibonding orbitals. So here we have 2, 4, 2, 4, 5, 6. So 10 minus 6 is 4, and 1/2 of 4 is 2. So the bond order here would be 2. There would be a double bond. So you just have to remember the filling order. Did that answer your question or no?
Yeah, it sort of did, but I just think, like, you know how in 31 it's like how do I say? Oh, it's like empty, like the diagram.
It's like a what?
Like the diagram is empty, so I guess that's why I was confused.
Oh, for number 31. Yeah. I was going to use, yeah, right. I could have used this diagram for this, but yeah, that's okay. I went ahead and drew it. So this is a diagram here for the elements, for the diatomic elements, lithium and beryllium, okay? So based on this diagram, we're looking at lithium and we're looking at beryllium, okay? So lithium has how many electrons? What is the atomic number of lithium?
Three.
It's 3 electrons? Okay. Yeah. So we have 2, 3 electrons. So diatomic lithium is going to have 6 electrons. So we start here, we put 2, 4, 6. And it's asking us, yeah, you know, we'll look at the answer key here, or the answers. We look at the answer choices and they want to know basically what is the bond order, because that's how we determine if it's stable, okay? So the bond order, this is for lithium, diatomic lithium, is 2, 4, so it's 1/2. We have 4 minus, so we have 2 in this bonding orbital and 2 in this bonding orbital, so that's 4, and we have 2 in an anti-bonding orbital. 4 minus 2, 4, yeah. 4 minus 2 is 2, 1/2 of 2 is 1. So that's stable, but this is paramagnetic. There are no unpaired electrons, so it's paramagnetic. For the beryllium, how many electrons does the beryllium have?
4.
It has 4. So diatomic beryllium would have 8 electrons. So we have 2, 4, 6, here, 8. So now, look what happens. The bonding, we have 2 4 bonding electrons. So the bond order would be equal to 1/2. We have 4 minus, and then we have 2 4 electrons in the anti-bonding orbitals. The bonding order is 0. So we can say that this is not stable. And it's you know what? This should be diamagnetic.
I think lithium is diamagnetic.
Yeah, it is diamagnetic. So, and this is also, I mean, this wouldn't even form, but you know, so the beryllium is unstable. Okay, so the beryllium is unstable, and the lithium is stable. It has a bond order of 1. And it's diamagnetic. So D would be the correct answer here. Okay. Any questions on this one?
How did you do the lithium diagram one more time? You said you did the arrows.
So we have lithium has 3 electrons. We have diatomic lithium. So we distribute the 6, you know, that'd be 6 electrons, 2, 4, 6.
Mm-hmm.
And the bond order would be 1/2.
Mm-hmm.
And so we have 4 electrons in bonding orbitals, 2 electrons in anti-bonding orbitals. 4 minus 2 is 2. 1/2 of 2 is 1. Bond order of 1 is very stable. So it would be lithium is the diatomic lithium is stable, and it's diamagnetic because there are no unpaired electrons.
And the 1/2 is the where did that come from?
That's the formula
Oh,
for determining bond order. Yeah. So bond order is equal to 1/2 times the quantity of the number of bonding electrons minus the number of anti-bonding.
Okay, so this is kind of like chapter 6, but instead we're doing like actually like anti-bonding, and like the diagram is
Yeah,
different.
we're doing a different model.
Yeah.
Okay. What we learned in chapter 6 is the VESPR model. This
Yeah.
is molecular orbital theory, and this is the theory that you're going to be using in organic chemistry quite a bit.
Okay.
Okay, it gets more complex, but
Is that what the star is for? Is the anti-bonding order?
yes, it is.
Okay,
Yes.
thank you.
Exactly. You're welcome. Yes. Is that okay? You guys want to? Any more questions?
Yeah, so it's basically bonding minus anti-bonding.
Yes. 1/2 of the quantity of the bonding minus the anti-bonding electrons. Yeah. Okay. Of these substances here, these are the same substances down here. Only which one has London dispersion forces as its only intermolecular force? I'm going to check and see what my dogs are doing. They're very quiet. Let's see. What are you guys doing? What do you want, Layla? Where's Oliver? Okay, Layla? Layla, where are you? Layla? Layla, there you are. Otherwise, I'd bring it in. No, you're not coming back here. You little devil. You know, when we were teaching during the pandemic online, I used to teach back here in this office I have. And I used to bring Layla in with me, you know, and because my husband was teaching downstairs, and the dogs, she usually barks and carries on. But, you know, it's funny. She would never come back here, never ask to come back here after that. She, you know, it was every, 5 days a week. And now she wants to come back. But I have stuff on the floor that she can get into. So, yeah. Which one of these has only London dispersion forces? Oh, this one's easy. Which one? A, B, C, D, or E?
I think D as in dog.
I think you're right. It is D, and that's because methane. Layla, stop it. She's something else. The thing is, if she would sit on my lap, I'd let her back. But I've dropped a few things on the floor that I wasn't able to find, and I don't want her getting into it. So this is, we know that this is nonpolar. So the only intermolecular forces are London dispersion. The rest of these are all polar. So the methane is nonpolar. And that's because, well, for one thing, carbon-hydrogen bonds are nonpolar. So you've got to have at least one polar bond to have a polar molecule. Oh, this is a good one. Number 33, which of the following should have the lowest boiling point? Remember, the stronger the intermolecular forces, the higher the boiling point. The weaker the intermolecular forces, the lower the boiling point.
Would it be D as in dog?
Oh, let's see. D. Yeah, it would. And I'll tell you, okay. So I'm looking at.
This would be H2O, right?
Pardon me?
Like, if it asks for the highest boiling point, that would be H2O, right?
Yeah, because here's what you have. You have sulfur. Okay, so let's see. We have 6, 7, 8, 2, 4. So we have 2, 4. And we have the 2 lone pairs on the sulfur, right? So this is polar. It has dipole forces and London dispersion forces. But water, remember, water, that's a terrible looking water, but hey, it has, it has same structure, right? The only difference is we have an oxygen instead of a sulfur, but we have hydrogens bonded to the oxygen. So it has dipole, London dispersion, and hydrogen bonding. So this one is going to have the highest boiling point. So the answer is E. Oops, I erased the wrong one. So,
No, it's asking.
oh, you want to know which has the lowest boiling point? Oh, okay. Water has the highest. Let's see. We have the phosphorus. We have 3 hydrogens. And we have 5, 6, 7, 8, 2, 4, 6, 8. So a lone pair on there. And then we have the silicon. Yeah, this one here. Whoops. This one here is going to have a low boiling point because this has only London dispersion forces. This one here, this would have both dipole, and London dispersion forces. Let's see, the HCl we know is polar, right? Because the electrons are going to spend more time around the chlorine. So for number 33, this one here only has the London dispersion forces. So water would be would have the highest boiling point, and the silicon with the 4 hydrogens would have the lowest boiling point. And that's because it only has London dispersion forces. Number 34, how many more do we have to go? Oh my gosh, okay. Okay. Where are we going? Number 34. Which of the following molecules is hydrogen bonding likely to be the most significant component of the total intermolecular forces? So we have this, we have this, we have this, we have this, and this. So I'll tell you right now, the only molecules that have hydrogen bonding are this one, and this one. Okay. So this one here, C, would be the correct answer. And that's because you have 1 carbon and the 4 hydrogens and the oxygen. So this one would have the most significant hydrogen bonding. This one here, you have 5 carbons there. So there's going to be, there's going to be significant London dispersion forces as well because of that 5 carbons. Remember what I told you. Anything that has, usually more than 3 carbons is going to be much less polar, okay? So when you have, 4 or more carbons, then you're going to have significant London dispersion as well as some hydrogen bonding. So actually C would be the correct answer for number 34, okay? Use the given average bond dissociation energies to estimate delta H for the reaction of methane with fluorine according to the equation. Okay, as I said, you should always, my little Layla is really persistent. She's just scratching me. She's such a little, oh, she's funny. So we have the 2 fluorines, okay? Those have I'm just including the electrons just to show you. Let's get more practice for the drawing the list. Then we have the CF4, so the carbon tetrafluoride. So we have 4. I won't put the electrons on the fluorines. And then we have 2, and then we have the diatomic hydrogen. Okay, so what we're going to do is we're going to take the bond dissociation energies for the reactants. We have 4 moles of carbon hydrogen bonds. We'll multiply that by 410 kilojoules per mole. And then we have 2 moles of the fluorine, so 2 moles. That's the fluorine. And that's going to be multiplied by 158 kilojoules per mole. Okay, I'll put this in, and then we'll subtract from that the products. I have 1, 2, 3, 4 moles of the carbon fluorine bonds, and we'll multiply that by 450 kilojoules per mole. And then I have 2 of the hydrogen bonds, so 2 moles of the hydrogen, and we'll multiply that by 436 kilojoules per mole. Okay, so now I'm going to put this into the calculator. 4 times 410. Oh, what happened here? Oh no.
I have a question.
Yeah.
So usually we're doing like products minus reactants, but then how come in this case we're doing the reactants minus the products?
Actually, you could do products minus reactants, but what you'd have to do is you'd have to put a negative sign on the product bond dissociation energies. And that's because when bonds form, there's a release of energy. Okay, so
when it's saying D, like capital D, like that's like you should know that you're actually doing the reactants minus the products.
Yeah, you can do it either way, but you've got, okay, but when you do products minus reactants, you got to make sure that you put a negative sign on those bond dissociation energies. Okay?
Okay.
Because look, this, okay, so this is going to be equal to delta H, right?
Yeah.
So this is equal to delta H. But again, you'd have to have negative signs for the products and positive sign for the bond dissociation energies of the reactants. Okay? So do it either way. This way, when we take the products or the reactants minus the products, it kind of takes care of not having to worry about the negative sign. Okay?
Yeah, that's true.
Let me grab my water real quick. Yeah, so that's what that is. What are you doing? Okay. I got my water and I got some chocolate. All right, so I was putting this into the calculator. Let's see, what did I have? Okay, so we have 4 times 410 plus 2 times 158. And we'll subtract from that 4 times 450 and plus 2 times 436. Okay, I get a negative 716 kilojoules. So, I'll show you guys that you can also do it. So that'd be a negative 716 kilojoules, okay? Now, if I were to do products, I would just say, okay, I have 4 moles of the carbon-fluorine bonds times a negative 450 kilojoules per mole. And then I would have plus 2 moles of the hydrogen bonds times a negative 436 kilojoules per mole. So I'm going to go ahead and put this in brackets, and I would subtract from that. This part, the reactants, okay? So when you do that, you still get, I'll take 4 times a negative 450 plus 2 times, 2 times a negative 436, and I'll subtract from that 4 times 410. I don't put a negative sign in front of those, plus 2 times 158, okay? And, oh God, I put something in wrong, but I should get the same answer, okay? Should be a negative 716 kilojoules. What is the molecular geometry of the sulfur tetrachloride?
B.
Oh, B. So sulfur tetrachloride, that would be B. So let me show you guys. What you would do is, again, you would draw the Lewis structure. So we have the sulfur, and we have the 1, 2, 3, 4. So we'll put the chlorines in like so. And let's see, we'd have 4 times 7 is 28 plus 6. We have 34 electrons to distribute. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons. And then I have a lone pair on the sulfur. So this is a trigonal bipyramidal electron pair geometry, but because of the lone pair, we have a seesaw molecular geometry. Good. Oh, here we're asked to determine the sign of delta F for each of the following reactions. So here we're going from a solid to a liquid. So with delta S, would it be negative or positive?
Positive.
Yep. And here we're going from 3 moles of gas to 2 moles of gas. So delta S would be negative.
So if in any case, if there's more reactants than products, then it would be negative, right? Or it would decrease.
For the gases,
yeah.
If there's a change in the number of moles of gases, yeah, then it'd either increase or it'd either be negative or positive. In this case, it's negative because we've gone from 3 moles to 2 moles, so there's less freedom of motion.
Okay.
Professor?
Yeah.
I'm just making sure. Is this going to be posted tonight or tomorrow?
The answer key?
No, just this. Is this recording going to be posted?
It'll post. I don't know how long it'll take to post it, but it'll post.
Where does it get posted?
let me see here. Let me show you guys. Well, you have to go, what you do is you go into Blackboard Collaborate and you don't join a session. You go up to the upper left-hand corner and you see a menu there. It has 3 horizontal lines. Click on that and then click recording. Okay, I have a video in the Start Here folder on how to navigate Blackboard, or yeah, Blackboard Collaborate. So towards the end of the video, I show how to access the recordings. Okay, so this will probably take, I don't know how long it'll take, maybe a half hour for it to post. It's a long video, so I don't think it'll take longer than a half hour.
Okay, thank you.
This one here wants us to calculate delta G and tell us whether it's spontaneous or non-spontaneous. Okay, so delta G is delta H minus temperature times delta S. So the temperature is 25 degrees Celsius. Temperature must be in Kelvin, so that's 298 Kelvin. And let's see, the answers are in kilojoules. So delta S is always given in joules per mole. Delta H is always given in kilojoules per mole. So we'll just convert the delta S to kilojoules per mole. So delta G is delta H, that's a negative 1056 kilojoules per mole, minus 298 Kelvin times a negative 0.505 kilojoules per mole. That should be this should be joules per mole Kelvin. Okay, so that'd
I
be,
just multiply the negative 1056 by 1,000 so that it could be the same.
pardon me?
Like, you know how they're both different? All I did, I multiplied negative 1056 by 1,000 to get it into joules.
Yeah, the only reason I'm putting it into kilojoules or the delta S into kilojoules is because the answer is in kilojoules. So these units have to agree. Okay, so they do have to agree. So Kelvin cancels out. Okay, so our answer is actually going to be in kilojoules. Kilojoules per mole. So we have a negative 1056 minus 298 times a negative 0.505.
Wouldn't you do negative 298 multiplied by the enthalpy first? Or sorry, the entropy?
That's what we're doing here. This is delta H minus the temperature times delta S.
Were you subtracting or multiplying first?
I'm just putting it into my calculator. So I've got a negative 1056 minus 298 times a negative 0.505. And I get a negative 906. I get a negative 906 kilojoules per mole. So delta G is negative, so the process is spontaneous, and it's a negative 906 kilojoules. So the answer for this one would be D. Okay.
So if it's greater than, if delta G is greater than 0, then it would be non-spontaneous.
Exactly.
So if it's equal to 0, would it be equilibrium?
Yes, it would. Absolutely.
Okay.
Mhm. Yeah. There'd be no net change because the system is
Yeah, that's what I meant.
Mm-hmm. Yeah. Okay. Okay. Let's you know what? I'm gonna have to skip some of these. But let's see. We did this in class. We did a problem like this in class. Number 40. I have to get up in the morning early. I'm not a morning person, so I have to. Oh, where are we at now? Oh my gosh.
40.
Okay. Yeah, number 40 would be A. You'd have a straight line. Yeah. So it'd be linear. So that'd be A. Let's see, number 41. Equal volumes of different gases at the same temperature and pressure contain the same molar amounts as another way of stating which law?
D.
Yep, Avogadro's law, right? That always has to do with the number of moles of gas. Okay. Oh, let's see. The volume of 350 milliliters of gas at 25 degrees is decreased to 250 milliliters at constant pressure. What is the final temperature of gas? So we're looking at volume and temperature. So V1 over T1 is V2 over T2. So V1 is 350 milliliters. T1 is 25 degrees, so that's 298 Kelvin. V2 is, you guys asked some really good questions tonight. That was great. So we're looking for T2. So we'll solve this for T2. So T2.
Could we also use the equation like V2 over V1 equals T2 over T1?
Can you repeat that? I'm sorry.
Oh, sorry. Can we also use the equation V2 over V1 equals T2 over T1?
V2 over V1?
Yeah.
Is equal to?
T2 over T1.
I mean, let's see. So you're saying, no, you can't. No. You want V1 over T2 is equal to V2 over T1?
No. V2 over No, I was saying V2 over V1.
V2 over V1?
Yeah.
I mean, you could put V2 over V1. Yeah.
Okay, and then the same with T2 over T1.
And then T2 over T1. Yeah.
Okay.
I mean, you could do these problems 100 different ways, you know?
Yeah.
But so I'm just going to do it this way. T2 is going to be equal to V2 T1 over V1. And then you just plug everything in. So V2 is 250 milliliters, T1 is 298 Kelvin, and V1 is 350 milliliters. So milliliters cancel. And we should be left with, or we are left with Kelvin. So yeah, I mean, you can rearrange the equation as long as you rearrange it correctly. Yeah, definitely. Yeah. 250 times 298 divided by 350. I get 213 Kelvin. I get 213 Kelvin. 213 Kelvin. Notice the answers are in degrees Celsius, so I need to convert the 213 Kelvin to degrees Celsius. So 273 minus 213, that gives us,
Wouldn't you do 213 minus 273 because it has to be a negative?
well, you take, okay, so we have Kelvin is degrees Celsius plus 273. And so the Kelvin temperature, it'd be the 213 minus the what did I say? 273 minus 213? No, it should be the 213 minus the 273 would give us the degrees Celsius. So that'd be 213 minus 273, and that'd give us a negative 60 degrees Celsius. Negative 60 degrees Celsius. Yeah, sorry about that. I said the wrong thing. So a negative 60 degrees Celsius.
It's okay.
Yeah. Okay. What is the value of the gas constant in units of millimeters of mercury, centimeters per mole Kelvin? Let me see we'll see if we can go back to this one. Basically, you know, you would use the universal gas constant, the 0.0821 liters atmospheres over moles Kelvin. So you'd need to, the volume you would change to cubic centimeters. The pressure you would change to millimeters of mercury. Okay.
So would it be 760? Like the pressure.
Oh, yeah, because 1 atmosphere is equal to 760 millimeters of mercury, right?
So if we're given like a number and we have to divide it, we do the number divided by 760, right? Like
yeah, what you would do is you would so we have the point. Okay, so here we have our units. So I would say, okay, 1 atmosphere is 760 millimeters of mercury. And then as far as the liters go, 1 liter is 1,000 cubic centimeters. Okay, so this would cancel out liters, and this would cancel out the atmospheres. So yeah, might as well do this one. 0.0821 times 760 times 1,000. So that'd give us 62,396. Well, that'd be cubic centimeters, well, millimeters of mercury, cubic centimeters per mole Kelvin. So this would be 6.24 times 10 to the 4th. So 6.2. Oh, they kept, they kept 6.23. Yeah, it depends on the conversion factors you use, but it'd be 6.23 times 10 to the 4th millimeters of mercury, cubic centimeters per mole Kelvin. So the answer here would be C.
Thank you.
You're welcome. At standard temperature and pressure, how many liters of ammonia can be produced? Okay, from the reaction of 6 moles of nitrogen with 6 moles of, of hydrogen. So make sure the equation is balanced. We need to find the number of moles of ammonia. Oh my gosh, this is one of those problems where we're given the amounts we have to find our limiting reactant. Okay, so let's do that. Let me erase all this stuff here. Okay, here we go. How many people are left? Oh, 12. Okay. Well, I guess that, we've been on here a little over 2 hours, but still, it's fun. I like doing this. I like doing the review sessions, and you guys are asking some great questions. So we have 6 moles of nitrogen and 1 mole of nitrogen will form 2 moles of ammonia. So 6 times 2 would be 12 moles of ammonia. And then we have 6 moles of hydrogen. And this is actually a pretty good review here. Times 3 moles of hydrogen produce 2 moles of ammonia. And what we have is 6 times 2 is 12 divided by 3 is 4 moles of ammonia. So this is our limiting reactant. So our hydrogen is limiting. So the most we can make is 4 moles of ammonia. So now they want to know how many liters of ammonia can be produced. So we'll use our ideal gas law. And this is a standard temperature and pressure. So pressure is 1 atmosphere, temperature is 273 Kelvin. And we'll solve this for volume. So the volume is nRT divided by the pressure. So number of moles is 4 moles. Okay. Times R, which is 0.0821 liters atmospheres per mole Kelvin, times the temperature. What is the temperature? Oh, okay. 273 Kelvin divided by the pressure, which is 1 atmosphere. So let's see. Oh, I should have used more significant figures here. That's okay. I'm getting kind of sloppy now because I'm tired. 4 times 0.0821 times, oh darn, 273 divided by, I have 89.6, actually 89.7 liters. So that'd be that one there. Okay. Let's okay, this one here, yeah, we have the 0.5 gram sample of silver oxide. It's heated, and the silver oxide decomposes to silver, solid silver, and oxygen gas. Oh, this is one that's collected over water. So 6.9 milliliters of the gas is collected over water at 27 degrees Celsius. And 1 atmosphere external pressure. What is the percentage of silver oxide in the sample? And then we're given the partial pressure of the water. Yeah. So what you need to do, for this one, you would subtract the partial pressure of the water from the 1 atmosphere. You'd have to convert it to atmospheres. And then what you would do is find you have the volume of the oxygen, you'd find the number of moles of oxygen, and then from there, this one has a lot of steps. You know what? I'm going to pass on this one. You won't get anything like this one on the exam. This one, I mean, I would do it, but I'm getting really, really tired. Let's see what else is here. How many molecules of nitrogen are in a 250 milliliter container at 780 milligrams of mercury and 135 degrees Celsius? So basically what you need to do is use this PV equal to nRT, our ideal gas law. We're going to go ahead and solve for the number of moles. So it'd be PV over RT. So you'd solve for the number of moles of nitrogen. Yeah, we can do that. Let's see. The pressure is 780 millimeters of mercury. We have to convert that to atmosphere. So it'd be 760 millimeters of mercury is 1 atmosphere. And then times the volume. That'd be 250 milliliters is 0.25 liters. And then divide by 0.0821 liters atmospheres per mole Kelvin times the temperature. That's 135 degrees Celsius. So that'd be plus 273. That'd be times 408 Kelvin. So the number of moles would be 780. Can't read my own writing. Divided by 760 times 0.25. And then we'll divide that by 0.0821 times 408. Oh no, what happened here? Oh. Okay, let's see. Oh, you know, I should put a parenthesis in here. Okay, so I get the number of moles as 0.00766 moles. So now we would convert this to the number of nitrogen molecules. 1 mole is 6.02 times 10 to the 23rd molecules. So that'd be times 6.02. Oh, no, that's not what I wanted. Oh. Okay. Times 6.02 to the 23rd. And I get 4.61. I get 4.61 times 10 to the 21 molecules. So they're just doing different. The answer here would be D. Okay. There's a certain one I'm looking for. I don't remember if it's here, but let's see. A 1 liter flask. What is the total pressure? Oh, okay. Remember, total pressure is equal to the partial pressures of the component gases. This one has 2 component gases. It has 0.2 moles of hydrogen and 0.215 moles of nitrogen. And so what we would need the 2 partial pressures. So we have a 10 liter flask. at 20 degrees Celsius. Okay, so we want the partial pressure. Okay, so let's do the partial pressure of hydrogen. So that'd be 0.2 moles times 0.0821 liters atmospheres over moles Kelvin, and that'd be times the temperature, which is 20 degrees. So that'd be 293 Kelvin. That'd be times, come back here, times 293 Kelvin divided by 0.125 liters. So the partial, let's see, that'd be 0.2 times 0.0821 times 293 divided by 0.125. So partial pressure would be, wow, that's huge. It'd be 30.
Yeah. You used the volume of 49 instead of 48.
A volume of 49.
That one has 125 milliliters.
Oh, it's 10 liters. Okay, I was reading this problem here. Okay. Okay, so that should be 10 liters. Yeah, that'd be 10 liters. I was reading the problem underneath it. Okay, 10 liters. Okay. Yeah, I was going to say that. Yeah, wasn't good. 0.2 times 0.0821 times 293 divided by 10. Yeah, that looks a little bit better. So that'd be 0.48 atmospheres. You do the same for the nitrogen. So the nitrogen, that would be, why do I keep reading the wrong problem? 0.215 times 0.0821 times 293 divided by 10. So that'd be 0.517 atmospheres. So they want the total pressure, so we just add the 2.481. And again, there are different ways that you could do this one. 0.517. So that'd be I get 0.998. So the total pressure is 0.998 atmospheres. Okay, there we go. There's that one. Okay. Oh, let's see. Well, we might as well finish this up. Okay, so a 0.429 gram sample of gas occupies 125 milliliters at 60 centimeters of mercury and 25 degrees Celsius. What is the molar mass of the gas? Yeah, so we have pressure times volume is equal to nRT, and N is equal to the mass in grams over the molar mass, right? So I'm going to substitute that in for N. I always have to derive these. I don't remember them. And that's times RT. And the molar mass is equal to the mass times R times T over pressure times volume. Okay. So what are we being asked? Okay, so molar mass. So the mass of the sample is 0.429 grams times R, 0.0821 liters, atmospheres over mole Kelvin. Okay, times the temperature. Wait, where are we at? Wait. Times the temperature, which is 298 Kelvin. And then we're going to divide that times the pressure, 60 centimeters of mercury. And we have 1 centimeter. 1 centimeter is equal to 10 millimeters. Okay, that's our pressure times our volume, and this one is 125 milliliters, so it's 0.125 liters. And this should give us the molar mass. You can see, well, we see these cancel. Volume cancels. Oh, there's something I didn't do here. I have to convert millimeters of mercury to atmosphere. So 760 millimeters is 1 atmosphere. Okay, times the 0.125 liters. Okay, that's better. That's why it's really good to always use your units. Okay, put your units in. Let's see. Kelvin, that cancels. Liters cancel, and we're left with grams per mole. So this will give us our oh dear, this will give us our molar mass. So 0.429 times 0.0821 times 298, and that's going to be divided by, we have 60 times 10 divided by 760 times 0.125. And I get 106 grams per mole. And there it is. Okay. How many are left? 8 people. Good. Okay. You guys want me to do the other 2?
No, it's okay.
Are you sure? I will. And we can finish them. I'm going to do them in case somebody wants to see them. If you guys all disappear, then I hope this was helpful tonight.
It was. Thank you for being here.
Oh, you're welcome. Let's see. Let's see. Which of the following would have a density of 1.89 grams per liter at 7 degrees Celsius and 987, or not 900, 0.987 atmospheres? Okay, I'm going to have to, let's see, PV is nRT, and yeah, and N is equal to the mass over the molar mass, and then we have the volume times the volume, and then this is RT. So mass over volume is the density, so the pressure is equal to the density times RT divided by the molar mass. And the density, we'll just solve it for density. Density is equal to the pressure times the molar mass over RT. Okay, so the temperature is 273 plus 7, so temperature is 280 Kelvin, and oh good, we're in atmospheres. Okay, and wants to know which should have a density of 1.89 grams per liter. Now, there are a couple of different ways too that you could do this. I'm wondering, we can make this 1.89. Yeah, but you'd still, you know what? Let's do it this way. Let's go ahead and solve for the molar mass. Or no, yeah, we can solve for the molar mass. Oh yeah, this would be much easier. Molar mass is equal to the density times R times T divided by the pressure. Okay, so if we solve for the molar mass, then we can determine which substance it is. Yeah, that's a good way to do this. So the molar mass, the density is 1.89 grams per liter times R, 0.0821 liters atmospheres per mole Kelvin, times 280 Kelvin divided by 0.987 atmospheres. Yeah, this is good. Yeah, this is very good. So 1.89 times 0.0821 times 280 divided by 0.987, not 981. And I know exactly which one it is. So the molar mass is equal to 44.02 grams per mole. So this one would be carbon dioxide. So carbon dioxide. So that was an easy way to do it. So the answer for that one is B. And then we have one more to do. Okay. 7 of you are sticking with, well, 6 of you are sticking with me. Okay. Oh, let's see. Oh, this is another stoichiometry one. Okay. So let me erase this. Is everybody still awake?
Yes.
I'm putting you to sleep and you guys are keeping me awake, right? So that's usually how it goes. Okay, this one's another, this will be fun to do too. Okay. Ooh, how many liters of oxygen are needed to react with 55.6 grams of methane at standard temperature and pressure? Good. So we have 55, this is similar to the first one we did, grams of methane. We'll convert that to moles of methane. So let's see, we have 12.011 plus 4 times 1.00794. So that's 16.04 grams per 1 mole of methane. So we need to know the number of moles of oxygen. So we'll use our mole ratios. So 1 mole of methane, come on, reacts with 2 moles of oxygen. So we have 55.6 divided by 16.04. times 2, and that is 6.93 moles of oxygen. So now we'll just solve for volume, the ideal gas law, and N is 6.93 moles times R. See, this is how you get to know R. You just do these problems, all these problems. 0.0821 liters atmospheres per mole Kelvin times the temperature. Oh, good. Standard temperature and pressure, 273 Kelvin, divided by 1 atmosphere. Great. Yes. So 6.93 times 0.0821 times 273. And I get 155 liters. So that'd be closest to that, B, 156. Sometimes that last digit will differ depending on how many, depending on how many digits are used for each of the variables. Any questions? Anyone have a question before we go?
Can you last time write the equation for bomb calorimeter and the other calorimeter?
Well, basically, for coffee cup calorimetry, you're looking for Q, and that's equal to the mass times the specific heat capacity times delta T. Okay, and then for the bomb calorimeter, you're going to, it depends on what you're given in the problem. You would be, the heat of reaction, it could be, it depends if you're, have water in the calorimeter, and you've also got to have the you got to have the, oh my gosh, I can't remember what it's called. The, oh my goodness, I just went blank here. You've also got to have the, oh my goodness, I'm sorry. I don't remember what it's called. I can't think of it.
Is it combustion?
Well, in a bomb calorimeter, that's what you're looking at. You're looking at a combustion reaction, okay?
Okay.
So you need the heat capacity of the calorimeter, and then plus maybe you're given the water, the temperature change, and the mass of water. But, both the calorimeter, and if there's water in there, both the water and the calorimeter are going to absorb heat from the combustion reaction, right? Because a combustion reaction is always exothermic. Okay?
Yeah. Got it. Thank you.
Oh, you're welcome. Anybody else have a question? Anyone? Okay. Well, Asma, Dima, Avelina, Jordan, and Krisha, thank you very much for sticking around.
Thank you, Dr. O'Connor. Have a great night.
You too. You're welcome.
Thank you.
You are very welcome. So everybody have a good night. I'm now going to take my dogs out. Okay.
Have fun.
Okay, we will. Bye-bye. Thank you, Avelina. Okay, so I'm gonna, I have to stop recording.